And so that means these are hard to oxidize. Gold, copper, gold, copper, what else? Silver, nickel. Those are pretty hard elements to oxidize. Nickel to a lesser degree. H plus is an OA, chloride is an RA, water is both an OA and RA. And so, we don't really think, we just go through the steps. The steps are always the same. You do one, you've done them all, right? Because the steps are the same. All right, this one's trickier because gold does not appear on our list, does it? No, so we have to search. Gold, does that mean it's totally unreactive? No, we have to search. And where we find gold is in Appendix D. Appendix D, you have many pages of what we call half reactions. And so if we go to Appendix D, then we say, oh yeah, gold can react as a reducing agent. And do I have to know? No, I just copy it down. Gold goes to gold 3+. And so here, we just try to rank these. What's the strongest reducing agent? Gold, chloride, or water? If you have Appendix D out, just take a look. What's the strongest reducing agent? Start at lithium and this work. Wait.
I'm guessing it's chloride.
Chloride?
Yes.
I don't want. You don't have to guess. You just look at the chart.
Water. Right now. Water's
Maybe we should take a look at Appendix D.
Sure. That'd be really awesome.
All right, while I'm waiting for this computer, we'll come back to this problem, but are there other questions before we get started? Just the potassium bromide. Did we do that one yesterday?
We talked about a little bit that the sodium reacts with the water, right?
Yes.
You talked about it.
Okay, the sodium, yeah, that one's meant to see if you're just married to the single replacement pattern, which a lot of people are, but you have to, basically you have to adopt the chart method in order to solve that. All right, go ahead, Scott. Decomposition of KCl3?
Gas formation, like but I know that it's changing the oxidation state. Does that mean we have to do it as a redox?
It is a redox. You can't list gas formation as the sole driving force. In redox, gas formation is not enough. Gas formation helps. It helps all reactions, right? But in redox, there are other factors that could prevent it from occurring. And so that KClO3 decomposition, the driving force for that is going from stronger to weaker, OA, RA, And the gas formation is not enough. Gas formation is never enough for redox by itself. By itself. The example, do you recall what example I gave to show that gas formation is not enough for redox? Not the bicarbonate, because the bicarbonate's actually acid base. Yeah. The one that I gave for this is, some people will tell me that water will decompose because of gas formation. So gas formation is the driving force for the decomposition of water. So we're going to form plenty of gas, hydrogen and oxygen gas. The problem is it's not enough. Gas formation, because what we're doing is, in addition to producing a gas, and metathesis and acid base, if you carefully look at those, you know, all the oxidation states are staying the same. So you're just looking for favorable combinations in both, you know, acid base and a favorable combination in acid base is producing a weaker acid and base, which has a stronger bond. A favorable combination in metathesis is forming a precipitate, which has a stronger bond. You know, a weaker acid, which has a stronger bond than a stronger acid. Forming a gas. A gas can help in different ways. Gases usually have strong bonds, and number two, when you drive off the gases, there's something called Le Chatelier's principle that helps drive the reaction forward. But here, even if we use Le Chatelier's principle, even if we put a vacuum above a cup of water to suck away any gas that's formed so that it can drive this reaction forward, it's not going to happen because the change in the oxidation states is just way too great. I mean, in other words, we're going from something very stable to something very unstable. This is like, I always ask, what would you rather fill the trunk of your car? Well, neither probably, but a gallon of water or a gallon of hydrogen, you know, and oxygen. You know, I was at a conference and this guy was telling me he just got the new car, the Mercedes-Benz fuel cell car. Have you heard of that? Yeah, and what they have is they have a tank of 600 atmospheres of hydrogen gas. And I thought, how can you drive with 600 atmospheres of hydrogen gas? That's like a ticking time bomb in the car. And I said, what if you get in an accident and the hydrogen leaks out? You know, I just filled, you know, like a half a liter of hydrogen in that balloon. It wasn't that much. But you're talking about, you know, 600 atmospheres is a huge number of liters at atmospheric pressure. It's very dangerous. And so he said, well, before he bought the car, he saw that what they did was, this is for dramatic effect, but they took a tank, you know, the cylinder, flew it up in some 747 and dropped it from like 10,000 feet, or I forgot what it was, 30,000 feet into the desert floor, and it didn't rupture. And so he said after he saw that, then it was okay, because that tank reached terminal velocity, something like that. But still, you know, you're thinking, wow. Well, anyway, it's because you don't want hydrogen and oxygen. We call this, do you guys remember total energy? This is chapter 7. Total energy is equal to what? The total energy, if I want the total energy of water versus the total energy of hydrogen and oxygen gas mixture, what's the total energy equal to? The total energy is equal to, this is, maybe it's more physics. In physics, you learn the total energy is equal to, any physics people? Is equal to potential energy and kinetic energy. So the kinetic energy, we usually fix that at 25 degrees C. So this is potential energy. We call this a chemical potential. The chemical potential energy, this is like having a huge lead brick above your head, right? Whereas water is like standing on top of a solid lead surface, right? And so water has low energy, hydrogen and oxygen. You take that lead brick off the ground and raise it above your head like 100 feet and then just wait for somebody to cut the rope. You know, this is high chemical potential energy. This is very dangerous. And so we can't use gas formation because gas formation is, we aren't taking into account the change in the oxidation states. The change in the oxidation states is, it will totally change the behavior of the specific element. Right? This is a question I ask Chem 1A all the time. Why are redox reactions in general much more energetic, much more violent than acid-base or metathesis? I don't ask it in those terms, but imply it. Yeah, because you know, in acid-base, we're just looking at bond energies, you know, and the difference in bond energies between the product and reactants. Here we're looking at something more. So anyway, getting back to KClO3, that's a redox. How can you tell it's a redox? Because the oxidation states change. A redox always has the same driving force. This is why, you know, that doesn't go for all decomposition. You know, this decomposition reaction,
Supercarbon.
this is not a redox. The decomposition of carbonic acid into CO2 and water is not redox. That's just The driving force for this is gas formation, stronger to weaker acid, kind of thing. You know. Gas formation drives this, no problem. None of the oxidation states change. The oxidation states are all the same. Yeah.
In the case of potassium chlorate,
What's that?
in the case of potassium chlorate, you just separated it and then looked at the oxidation states to see if it was.
No, in the case of potassium chlorate, I just do the oxidation states based on the formula. I don't write out the structure for potassium chlorate. You don't have to do everything based on the structure. But when you look at potassium chlorate, which goes first? Well, potassium ions at +1, oxygen at -2, chlorine is at -6 +1. This has got to be +5. +5 on chlorine. We saw +5 on phosphorus and phosphate. +5 on phosphorus and phosphate's no big deal. It wasn't a powerful oxidizer. But +5 on chlorine is very unhappy chlorine. Because chlorine likes to be chloride, right, with -1. And chlorine's very electronegative. It doesn't want to lose electrons, so this is very powerful oxidizer, potassium chlorate. This is very dangerous stuff, actually. This is a powerful oxidizer.
I watched a video on potassium chlorate and sugar. It's really, really violent.
Yeah, potassium chlorate and sugar is quite violent. We could do that one. That one's a good reaction to do. But anyway, potassium chloride, when it decomposes, we form potassium chloride plus O2 gas. And so here, the chlorine, yes, it went from +5 to -1. -1 is its happy state, right? Chloride's very stable. Well, how do you know? Like table salt. Is table salt a very good oxidizer, reducer? No. And so chlorine goes to -1 and oxygen goes to 0. So essentially chlorine is very unhappy. It's going to take the electrons from the oxygen, its neighbor. Actually, it's bonded to it. And strip oxygen. Oxygen usually is very happy at -2. Think water, right? But chlorine's terribly unhappy at +5. And so we call this a very electron poor species. But you know, if oxygen is not an easy thing to oxide, you know, O2 minus, right? If there are easier things to oxidize like sugar, then for sure we'll just take it from sugar. You know, and this would just be an oxidizer rather than both. And so in potassium chlorate, the chlorine is the oxidizer in potassium chlorate, and the oxygen is the reducer in potassium chlorate. And so sometimes we have, and we saw this before, sometimes, you know, you have a reaction within the compound itself. You know, it could be a redox, it could be acid-base. When we saw carbonic acid formation. All right, other questions? Scott?
Well, the way we're supposed to do it, like inventory species, does it
All right.
really do it that?
No, this one doesn't do it that way.
Well, why? No.
It's not a solution.
No. What we have is, this is not a solution. This is a solid. This is a solid. And so when we inventory this, we get potassium in the solid state, potassium ions in the solid state.
No.
And then we have chlorate ions in the solid state. The solid state just means they're fixed in the lattice. You know, there's no translational. Solids have no translational motion. They still can have vibrational rotational motion, but they can't have translational motion. And so when we inventory, this is our inventory here, right? But this is more complex. Redox are more complex. Not everything you're going to be able to predict using the chart method. You know, the chart method is just one of the tools that you can use. And if it happens to be on the chart, then you can make a good prediction. But some things aren't on the chart, and some things are quite difficult to determine. So that's why we have the skeleton method. And the skeleton method is, some of these redox are very difficult to predict. Like, for example, I want you to tell me under what conditions I'm going to get, let's say, 10% carbon monoxide, 90% carbon dioxide from combustion. You know, how should I burn my methane to get 10% carbon monoxide and 90% carbon dioxide because I want to do a test? You know, a lot of people end up dying from their gas fixtures, from carbon monoxide poisoning, right? And so if I want to do some tests, I want to figure out what conditions I'm going to get some CO. CO, you don't want more than 10 ppm CO in any room. And so you tell me, am I getting more than 10 ppm or less than 10 ppm of CO from your Bunsen burner? Well, it depends on the condition. How much air you got in there, how yellow that flame is. If that flame is burning yellow because of lack of oxygen, then you're probably getting CO, and you're probably getting a lot of CO. You probably should stop and readjust the flame, right? But you tell me stoichiometrically or whatever how I can adjust the amount of CO easily. And so you go, that's easy. Theory can tell us that. No, it's not so easy. Theory doesn't easily tell us that. Right now I'm doing I have to give a little presentation about LEDs. When I was a graduate student, people were trying to get the blue LED. Did I tell you this? It was the red and the green. And was that easy? Somebody just said, oh, just mix this with that and you'll get the blue LED? No. And so a lot of these reactions are a bit complicated because, in fact, did you know that the combustion of methane wasn't well understood until about 20 years ago? I think about 20 years ago, somebody figured it out. And you go, what do you mean wasn't so well understood? I mean, it's really well understood. It's just methane plus 2 O2s yields CO2 plus 2 water. That's well understood, right? No, this is not. All you're seeing is the before and the after. You don't see the between, right? The between is, for example, what is that blue stuff in a methane flame? Somebody tell me what that blue stuff is. Well, somebody might say, oh, that's water, the ocean's blue. It's got to be water. Is it water?
No.
No, it's not water. And so what is that? And what's all the other stuff? What's a flame? Do you know what a flame is? A flame is the fourth state of matter. Fourth state of matter is plasma. Plasma is highly ionized gases. So if it's a highly ionized gas, what ions are in there? And so what I mean by it wasn't really well understood is nobody knew all the species and all the ways the collisions happen and the reactions. It turns out there are I think 1,000 or 2,000 possible collisions and pathways in this, something like that. And I'm exaggerating. Maybe it was a few hundred. I think it was 900. All the possible species present, And so reactions are very complex. This is why people are totally into like femtosecond. There's even something faster than a femtosecond laser. You know why they want such a fast laser? You know what a femtosecond is, right?
Yeah.
10 to the minus 15 seconds. Pulse of light. 10 to the minus 15 seconds. That means in 1 second, how many pulses are there?
A lot.
10 to the 15 pulses. 10 to the 15 is a trillion pulses of light in 1 second. Can you believe that?
Wow.
Is that right? Trillion, wait. Billion? No, it's a quadrillion. Wow. It's huge. And that isn't even the fastest. Now there's faster. What are they using the laser for? They need that fast pulses because some of these things have very short lifetimes. So if they want to observe it, they got to hit it quickly with light. And then they use spectroscopy, the absorption of light to determine what the species are. Either visible or vibrational or whatever spectroscopy. And so these reactions, in fact, biologists are very interested in this because, biologists want to know, what reacts with what. They just don't want the before and the after. They want, how things react, where the electrons go, well, the bonds are broken, this kind of stuff. So they're very into this kinetic stuff, this speed of reaction and all this other stuff because that gives you ideas about how the bonds are rearranged, what orbitals are involved, all this kind of stuff, that is so critical in understanding this. And so what we have is the two-pronged approach in chemistry. What is this two-pronged approach that I've been talking about? Theoretical and experimental. Good. Well, anyway, the two-pronged approach, theoretical and experimental. So a lot of reactions, we don't even bother thinking about the theoretical thing. We just mix it and see what happens, right? This is still done in all fields. For example, in pharmaceutical fields, they have a little plate, maybe it's about this big. In this plate, they do micro reactions. And so they can try 1,000 different combinations on a single plate and do those simultaneously. It saves a tremendous amount of time. If you were to do 1,000 reactions one at a time, it'd take you too long. The same thing in industry. They're trying to develop a catalyst, a better catalyst for, let's say, car exhaust. They don't just run one at a time. They'll do 1,000 different formulations all at once and see which one works the best, right? That's just trial and error. You just mix it and see what happens. Well, that's the same thing with the skeleton redox. You mix it and see what happens. You mix the main products and you see what the major, mix the main reactants and see what the major products are, right? And so, excuse me, so earlier, did I talk about wine? Wine being turned into vinegar? A little bit? Yeah, and so under what conditions will wine turn into vinegar, and what conditions will that ethanol be converted all the way to CO2? You could have the same reactant, it's the same reactant. Wine into vinegar is being converted by oxygen, right? That same reactant can convert that ethanol all the way to CO2, if you want, rather than into vinegar, acetic acid. And so it just depends on the conditions, the temperature, the pressure, all these things. And so normally when people do these reactions, they write all these things down, how long, how hot, how much pressure, how much concentration, all these things, because then they get this product. And so if you were to do this, we might not get CO2, we might get CO, we might get C. In Chem 4, they do an experiment where they starve the flame of oxygen, get a white crucible, put the white crucible on the yellow flame. Did you guys do this? And then look at the bottom of the crucible. The bottom of the crucible is coated with black soot. And so under those conditions of combustion, they didn't get CO2, they got soot. Well, how can we predict this? Did you learn any tools for predicting this? No, because this is kind of at the try it and see what happens phase, right?
Yeah.
It would be great if we could predict everything using theory, but unfortunately, the world is very complicated and the math of the theory is very complicated for even the simplest things. For hydrogen, the Schrodinger equation can be solved exactly. But for helium, can the Schrodinger equation be solved exactly? No. So if you can't solve it exactly, what do? You make
Different versions of it.
not conversions of it. You make approximations. Approximations are just simplifications that aren't always so accurate. Well, anyway, so a problem like this I thought was fair game, because you should have known what this forms. You should have known what this forms because this was the experiment 5 in Chem 1A. Decomposition of KClO3, you capture the O2, you measure the volume, etc. And so I thought you should know this one without doing the chart. So there's some things you just have memorized. All right, what else? All right, let's see if the computer...
Dr. Chow,
Yeah.
I'm having a lot of trouble reading the readout part. So can we read the readout chart together?
Yes.
All right. Wait, what kind of call will happen? What?
So we have to, I'm assuming, it's not including the things that are made to the same scale, so.
How many people have done the gold HCl completely? Golden HCl, no?
Yeah.
All right. You know what? We're going to have a quiz, but this quiz is it's going to be low pressure quiz because this is going to be open book, open notes, and you can work with other people in the class quiz. But why don't you do the golden HCl?
Yeah.
Gold occurs in two oxidation states, gold 1 and gold 3. Why did I pick gold 3? I picked it because gold 1 doesn't occur on this chart. Let's find it.
Gold 3's at 1.36.
Where is it?
1.36 plus.
Oh, okay, I missed it.
There you go.
It's on the bottom. There you go. Actually, 1.52. Do you see that?
Oh. Aqueous. Oh, I'm sorry. Yeah, you're right. It's this one.
Here it is.
Yeah.
All right, this is gold metal. Let's see, are there any other golds in here that are strong reducing agents? This is what I mean by you have to go through the entries because gold could occur again. If gold occurs again, then we need to fix that. But take a look at this. Is this gold as a reducing agent? No, this is gold 1 plus 1 reducing agent. So people who don't look at the entries will miss certain things. Oh, here's gold here. Do you see it? But it's not. Well, it's gold with chloride. Do we have chloride?
Yes.
Yes, we do. We have chloride present in the form of hydrochloric acid. So we could try this one and see. What else do we have? Is this one better than just gold alone? Yeah. In other words, gold alone is much less reactive than gold with chloride. Well, let's continue down here. But we inventory things. Okay, it's not here. I'm down to zinc, and definitely gold is worse than zinc as a reducing agent or less reactive. And so let me tell you how I inventory this, and then you finish it. Gold alone is a reducing agent, and so we have gold alone. But we also have gold with chloride as a reducing agent. And so we have gold and chloride together as a reducing agent. And then we have chloride alone as a reducing agent. And so chloride can be by itself as well. And then we have water as well. An OA and an RA. All right, so I'm going to give you, how much time? I'm going to give you 5 minutes or 10 minutes to finish this. I'll give you 10 minutes to finish this. Okay, it's going to be time. You can work with anybody you want or by yourself. And then you're going to turn this in. This is going to be worth 5 points.